lecture will be on chapter 3, which will focus on alkanes and stereochemistry. So hydrocarbons. Hydrocarbons are molecules that are made of carbon and hydrogen only. And so we've discussed some of this before. You have alkanes, alkynes, and aromatics. Alkanes have no double or triple bonds. Alkenes have double bonds. Alkynes have triple bonds. And aromatics are essentially structures like the benzene ring, in which you have alternating single and double bonds. And here are some examples. Now, alkanes have the general formula CnH2n plus 2. They're found in everything from natural gas to petroleum. The smaller alkanes have very low boiling points, and oftentimes exist as gases. As you can see here, methane, ethane, and propane, they're all gases. Here are some examples of alkanes, starting off with methane, the smallest unit of alkanes, all going up to neopentane, shown here. If you look at these examples, the CH2 group, that is the group that's in between or flanking two end groups that are CH3, these are called methylene groups. A series of compounds that differ only in the number of methylene groups is known as a homologous series. And so these are examples of homologous series. So if we look at the small alkanes, again, alkanes have the formula CnH2n plus 2. Start off with methane as the smallest, then ethane, propane, and butane, and you increases accordingly. And if you look at, for example, your table 3-2 in your textbook, you can get all of the formulas and physical properties of alkanes starting off with methane and going all the way down. And it'll show you what the number of carbons is, their structure, the formula, as well as the boiling points, melting points, and densities. As I mentioned before, short alkanes going up to propane and even butane are often as gases, and then as you increase the size, you start to see that they become liquids. So if we look at butane, C4H10, N-butane or normal butane, so normal butane or N-butane is hyphenated with an N that is italicized and then dash butane. This is just to tell you that it's normal butane, in which it's a linear chain. Here's an example of isobutane. Isobutane is essentially 3 CH3s surrounding by a CH mid group. These two are butanes, and as a result, they're constitutional isomers. Constitutional isomers are compounds with the same molecular formula, but the carbons are connected differently. Pentane, so as you increase in the size of carbons, the number of constitutional isomers increase. So as an example that's shown here, pentanes, C5H12, this is normal pentane, again, N is italicized in front of the pentane, isopentane, and then here's neopentane. And so all of these are pentanes, and as a result of different connectivities, they're constitutional isomers. Now, IUPAC, or the International Union of Pure and Applied Chemistry, developed a standard to name compounds, and this is an international standard so that everyone in the world uses it. What happens is it uses the longest chain of carbons as the main chains, and then common names are kept, such as methane, ethane, propane, and butane, etc. So if we look at the IUPAC rules, if we can go down the list. The first rule, or rule 1, is to find the longest continuous chain of carbon atoms and then use the name of this chain as the base name of the compound. Rule 2 is number the longest chain beginning with the end of the chain nearest a substituent. So if you can number it from left to right or right to left, you want to number it accordingly to wherever the substituent is closest to the left end or the right end. Rule 3 is that you want to name the groups attached to the longest chain as alkyl groups. Give the location of each alkyl group by the number of the main chain carbon atom to which it is attached. So you'll write the alkyl groups in alphabetical order regardless of the position on the chain when you're naming them. So as an example, we're going to go through the example and go through the rules. Rule 1, the main chain. Find the longest chain of consecutive carbons in this molecule here. So in this molecule, you can number it, you could have easily numbered it 1, 2, 3, 4, 5. But that is not necessarily the longest carbon chain. Rather, if you started up here, 1, 2, 3, 4, 5, 6, you would get a 6-carbon chain or a hexane. And so since this is the longest chain, you're going to circle this and this will be your parent chain. So when there are two longest chains of equal length, use the chain with the greatest number of substituents. So shown here are the same molecule in which you can find 1, 2, 3, 4, 5, 6, 7. 7-carbon chain if you circle it this way, or a 7-carbon chain if you circle it this way or identify it this way. So based on these two structures, which one is the correct structure? We choose this one because you have 1, 2, 3, 4 substituents off this main chain, whereas in this case you have 1, 2, 3 substituents off this main chain. So as a result, this is the main chain that you want to use, and you want to name accordingly. So an important thing to note is that when looking for the longest continuous chain to give the base name, look to find all the different chains of that length. Often the longest chain with the most substituents is not quite obvious, and that's what makes organic chemistry tricky. Rule 2 is numbering the main chain. So you want to number the longest chain beginning at the end of the chain nearest a substituent. So we have these are the same exact molecules. You could name it 1, 2, 3, 4, 5, 6, 7. I mean, number it in that direction, or you could have numbered it 1, 2, 3, 4, 5, 6, 7 in the opposite direction. So rather than choosing it here, if you chose it this way, you would have the first substituent be at number 3. But if you numbered it from the bottom end, the first substituent is number 2. As a result, this would be the one that you select in numbering, so that the numbering goes from bottom to top. And then you can put it together where you have the base name, which is heptane. You have 2-methyl, 4-methyl, 5-methyl, so that would be 2, 4, 5 trimethyl, and you'd have 3-ethyl. And then you would put it in alphabetical order where you have the ethyl, 3-ethyl, 2, 4, 5 trimethyl heptane. And so note that all of this is one word, and whenever you have numbers being put in, you want to put hyphens in between the numbers. Rule 3. Naming alkyl groups. So if you have alkyl groups coming off the main chain, right, you're going to follow the rule that if it's a CH3, it'll be a methyl group. If it's a CH2, CH3, like an ethane, it'll be an ethyl group. 3 would be propyl, 4 would be butyl, 5 would be pentyl. Sorry, this should have been pentane, so please correct that. There are common alkyl groups, right, as we had discussed, the methyl, ethyl, propyl group we had talked about, as well as the butyl group. But also under the category of propyl, you can have what is called an isopropyl group, which is a propyl group in which the substituent is coming off on the second carbon. You can have, in addition to the butyl group, the N-butyl group, you can have an isobutyl, kind of like the isopropyl, but in this case you have another methylene group. You can have sec butyl, which means secondary butyl. Again, here the substituent is coming off on the chain that comes on the chain in which on the chain of the butyl group of which is attached to the main chain. And this is a tert butyl group, or a tertiary butyl group, or T-butyl group. So note that anytime you have normal, it will be in italics, right, the N. Anytime you have secondary or sec, that will be italicized, and tertiary, that will also be, or tert, that will be italicized as well. So when writing your nomenclatures of molecules down, make sure that you use italics. And when you're in an exam and you're asked to write down the names of the molecules, I'd like you to also make sure that you point out that for example, sec is italicized. One way to do so is to underline it and tell me in your exam that is italics, because it's very hard for me and my TAs to tell whether you're using italics or whether it's your handwriting. So you need to be clear in order to get full points in an exam. Okay, so now we're going to apply the naming rules. So here's an example again. Again, you want to name the groups attached to the longest chain. So here's the longest chain. It's a 6-mer, so it's going to be a hexane. Give the location of each alkyl group by the number of the main chain carbon atom to which it is attached. So we're going to start numbering it from left to right, because at the 2 substituent, you'll start to see 2 position, you'll see a substituent. If you numbered it in the opposite direction, you would start with 3, and so you want the lowest number in terms of substituent. So this would be from left to right. And then you want to write the alkyl groups in alphabetical order, regardless of their position on the chain. So you have a methyl group at the 2 position and an ethyl group at the 4 position. So that means when you write it alphabetically. It'll become 4-ethyl 2-methylhexane. If you have multiple groups, when you have 2 or more of the same substituents, you want to use prefixes like di, tri, tetra to avoid having to name the alkyl group twice. So here's an example where you have a 10-mer as the base main chain, and then you have 3 methyl groups coming off. Again, it's numbered where the substituent is closest to the lowest number, so it's going to go from right to left. Here you have 2, 5, and 7-methyl trimethyl, so then it would be 2,5,7 trimethyldecaine. So let's do a problem. Give the structures of 4 isopropyl octane and 5 T-butyl decane. So the solution to this problem is you have 4 isopropyl octane has a chain length of 8 carbons, with an isopropyl group on the 4th carbon. So you're going to write out your CH groups until you hit 8. And then when you count to 4, at the 4 position, you're going to put an isopropyl. So you have to memorize those common names like isopropyl, isobutyl, neopentane, all of that. 5 tertiary butyl or T-butyl decane. So again, you're going to write out the decane. At the 5 position, you're going to put the tertiary butyl group, and so this would be how you write out the structure. You can have complex substituents. Complex alkyl groups are named by using the longest carbon chain. Carbon number 1 of the alkyl groups is the carbon attached to the main chain. So for example, if this is coming off a main chain shown on the left, and you have this complex substituent, you're going to name the main chain, which is the longest chain. In this case, it's the 3-propyl group. And so off of the 1 position, you're going to have ethyl. Off of the 2 position, you're going to have methyl. So this group will become a 1-ethyl 2-methylpropyl group. Here's another example in which the longest chain is 4, which is a butyl group. And then you'll have all of these methyl groups. So there's 1, 1. So this is di, and here's a tri. So it'll be 1, 1, 3 trimethyl butyl group. So let's do a problem. Give the IUPAC name for the following compound shown here. So what do? The first thing that you want to do is identify the longest carbon chain. And when you identify the longest carbon chain, as you do out multiple times, you see that this becomes your longest carbon chain, which is an 8-mer or octane. Now once you do that, you have to figure out which order will it go? Will it go 1 to 8 from left to right, or 1 to 8 from right to left? Again, you want the lowest substituent, meaning you want to have the substituent on the smallest number of carbon. So if we numbered it from 1 to 8, and in this case your first substituent would be here at 3, but if we name it this way as it's correct, the smallest substituent would be the first substituent would be at 2. And so this would be the way you would number it. Then you want to collect all of the substituents. You'll have 1, 2, 3, 4 methyl groups, right? So that'll be tetramethyl. And then at the 4 position, you have isopropyl. Now you have to put them in alphabetical order, so it becomes 4 isopropyl, 2, 2, 3, 6 tetramethyl octane. Note, all of the commas are put between each of the methyl groups, and then you put your hyphens after each and before each number when it's in the middle of the molecular name. An important thing to note is that when substituents are alphabetized, iso is used as part of the alkyl group name, but the hyphenated prefixes are not. So isobutyl is alphabetized with I, but N-butyl, tert-butyl, and sec-butyl are alphabetized with B. So this is something that you have to just memorize and know in order to do your naming of your molecules. So you can have various degrees of alkyl substitution. We talked about these complex alkyl groups. And so if we add these complex alkyl groups across the main chain, you're going to have to, again, name the main chain, figure out the ordering of the main chain, figure out what the substituents are. In this case, it's an easy substituent here, ethyl, but in this case, it becomes complex. So now you have to remember, when it's coming off the main chain, you number it 1, 2, 3. So this would be 1 ethyl, 2 methyl, propyl as a substituent, and then nonane. And then we'll put these all together so that it becomes 3 ethyl, 5 in parentheses, 1 ethyl, 2 methyl propyl, nonane. Here's another example in which the parent is the cyclooctane. In the case of the cyclooctane, you want to number it where you have most of the substituents at the lowest numbering possible. So number 1 would start where you have these 2 substituents coming off, 2, 3, and then 3, here's your substituent. That's a complex alkyl substituent in which you start numbering 1, 2, 3, 4 coming off of the main chain. So it'll be 1, 1, 3 dimethyl butyl cyclooctane, and this would be at the 3 position, and it's 1, 1 dimethyl. Boiling points of alkanes. As the number of carbons of the alkanes increase, the boiling point absolutely increases due to the larger surface area and increased van der Waals attractions. And shown here is the trend that as you're increasing the number of carbon atoms, you're increasing the boiling point. Same goes with isoalkanes. The trend for melting points of alkanes obeys the same trend as the boiling points. Melting points increases as the carbon chain increases as well. Alkanes with an even number of carbons have higher melting points than those with an odd number of carbons. So that's good to know. And that's why you can see this up and down behavior. In terms of alkane sources, alkanes are obtained usually from petroleum and petroleum byproducts. Fractional distillation will separate the crude oil into mixtures of alkanes with a range of boiling points. Catalytic cracking or hydrocracking is utilized to generate short chain alkyl or alkanes from long chain alkanes. So you can take long chain alkanes in the presence of hydrogen, heat, and catalyst. You can crack them so that you change them into or split them into smaller molecules. Catalytic cracking is without adding hydrogen, and it's just adding heat and catalyst. What this will do will indeed cut up the molecule, the long chain alkane, but it will produce it can produce alkenes because you're not adding hydrogen to the system. So this is a reaction you should note. So one of the reactions of many that you will be learning from this class. So let's look at methane, the alkane that is the smallest number of carbons. Methane is tetrahedral. It has sp3 hybrid carbon with angles of 109.5, as we've learned earlier. Methane is, in this case, is symmetric, so there's no stereochemistry. And we'll talk about stereochemistry later on. Ethane is comprised of two sp3 hybrid carbons, right? They're two connected to one another. There's rotation about this carbon-carbon sigma bond, and so there are conformations due to the rotation about this single bond. So if we look at conformations of ethane, here's the sp3 hybrid being shown and the overlap of the sigma bond, and you can see that this can rotate. So depending on the rotation, so you can see that these hydrogens are lying right on top of one another, but then you can rotate this so that it becomes staggered so that they're not necessarily on top of one another. Pure conformers can't be isolated in most cases because molecules are constantly rotating, even though these have kind of different molecular shapes because of rotation. Because they're rotating continuously, you can't necessarily isolate them as separate molecules. So one way to look at molecules in which you have rotation around the carbon-carbon bond is through Newman projection. So Newman projections, what you do is you take your eye and you're looking at ethane where you're looking at the central carbon. And when you look at that central carbon, this left hydrogen goes to the left of your eye, to the right of your eye is this hydrogen, and then right to the top becomes a hydrogen here. And then this hydrogen is to the right, this hydrogen's to your left, and this hydrogen going down is going down here. And this is a staggered Newman projection conformation where you're looking at your front and your back carbon and you're looking at it kind of barrel on. This is the best way to judge the stability of different conformations of a molecule. So we can look at kind of the potential energy of different conformations of ethane, as shown here. When the hydrogens are on top of one another in a Newman projection, this is called an eclipse conformation. This eclipse conformation is high in energy because, right, you're going to see electrostatic repulsion between these hydrogens with one another. As a result, you see an energy of 3 kcal per mole on the potential energy diagram. Now, if you stagger it by 60 degrees, shown here, right, you then get to a low energies where you don't see that repulsion or steric hindrance. And so we bring down the potential energy to near zero. Now if you turn it again, right, 120 degrees from where you started off with, now we're again eclipsed. And again, you're going to increase your energy to 3 kcal per mole. And then when you turn it again, right now you're all the way anti, meaning staggered, and these two hydrogens are anti to one another on opposite ends. You then go back to zero. So just by simple rotation from staggered to eclipse conformations, you can get this potential energy diagram. You should be able to actually make these, draw Newman projections based on molecules that I'll ask you to draw, and then also generate potential energy diagrams as you rotate across the bonds. Now propane. Propane has 3 carbons. So instead of a hydrogen on the bottom, that is being substituted by a methyl group. And so if we look at it and look at the Newman projection, this is a staggered conformation in which we have the methyl group on the bottom and then the other hydrogen on top and all the others staggered across. So this perspective is looking down at the C1-C2 bond. So if we look at propane conformations and try to draw a potential energy diagram for the conformations, we have the starting conformation being eclipsed. That starting conformation is now 3.3 kcal per mole because now it's a little bit more than 3.0 because now we have a methyl group, and that methyl group has hydrogens jutting out, so you're going to see steric interactions. If we stagger that 60 degrees, we see no steric repulsion, and as a result, loss in energy, or not loss in energy, but no potential energy. So it's good. And then we can eclipse it again by rotating another 120 degrees, and that'll also bring it up to here. So this stops here, and we're going to continue on with the next.